So again, coming back to the big O notations, assuming that we have fn 7n squared, then fn order of n n fourths or n cubic or n squared or n quadratic are all true, but this order of n cubic n quadratic or n squared is going to be the best answer because it is asymptotically tight. It's the equal growth rate. It has the equal growth rate and it's the asymptotically tight estimation. Okay. And let's look at this. And let's find out. These are all fn's. And let's find out the big O of these functions. And why don't you pause for a second and just write down your answer to these big O notations of these functions, and then let's find out. Okay. All right. Did you write down? Right. Let's start. And it's n squared slash 2 minus 3n. Right. It's going to be order of n squared because that this n squared dominates the growth rate of order of n, right? And in this case, right, order of n. And how about this case? It's very easy, right? It's order of n squared. How about this case? It's going to be, the tight answer is going to be, right, order of log n. Doesn't matter log 2 or log 2n or log 10n, it doesn't matter because you can always divide. And after the division, things become the constant, right? And how about sin n? Yes, it's going to be order of constant because sin n, really there is a bound, right? So it's going to be 1 and minus 1, and this is the sine wave. It's not going to go over than 1, so it's going to be constant long time. And 10 is, yeah, it's just constant, so order of n. You can always imagine this 1 is gn, this 1 is gn, right? And this log n is gn, right? And this gn, when we say big O notation, we add c, c multiply gn, right? And we compare this one, right? Do you recall the previous case, right? This characteristic. So because we have we are going to check this equation or inequalities. We can set up this C as we want. If we have C in a positive number, then we are safe. The goal is finding out C and there is nothing constrained, right? So given that if 10 is here and gn is 1, then we can just set this C equals 10, right? And here we can set this C equals something to match up this log n, right? And we can set up C equals like 7 or 8 or 9-ish, right? And we can do that. And even though this is a big number, it's still constant, right? Still constant. So we can say that it's an order of 1, order of constant. And log n compared to n, actually n grows faster. Why is that? Because log function looks like this and the linear function looks like this, right? This is n and this is log n. And n grows much faster, so it's going to be big O of n, right? So it's simple. And there are some rules of the big O notations. When considering the growth rate of a function using big O notation, ignore the lower order of terms and the coefficients of the highest order terms, right? Because this is because that we always multiply the constant C in terms of the the characteristic, the assumption satisfaction checking, right? And ignore the lower order terms. Why is that? Because that its growth rate is too small. So always the higher growth rate overtakes the lower growth rate terms. So if we can satisfy the higher growth rate term, the maximum growth rate term in that particular formula, then we can say that the sum function is the worst case of that given function, right? So when you have n squared, n cubic, then n squared, n means nothing in terms of the, or n squared means nothing in terms of the big O notations. And to judge this growth rate, you have to kind of remember the growth rate order. And growth rate order is like this. So this is the Cn and nk. This is called exponential. This is called polynomial, right? And here is all polynomial. This is called n log n. And this is called linear. And this is called logarithmic. And this is called constant, right? So the order is exponential and polynomial and log n and linear and the logarithmic and constant, right? Under these conditions. And you know you don't have to worry about the base of the logarithmic function, because this is eventually going to be the constant. If you just divide the particular log c with a certain base, right? So given this characteristics, there are some more theorems to this. One thing is that this Tn is equal to order of Fn and T2n is order of Gn. In that case, the plus means what? Max. Why is that? Because let's imagine this case. Order of n, we have order of n squared. In that case, we just want to find the maximum. The plus doesn't affect each other, right? So it's going to be this case program structures like for loop here and here, and this is a simple loop, and the another thing is for loop and, right? This is going to be very likely n squared. This is going to be n. In that case, in the worst case, the runtime growth rate, this is going to dominate the runtime growth rate, right? So this n squared is going to dominate. So by only considering this later part of the order of n squared actually answers this plus of the runtime. This plus of the runtime. Having said that, for instance, how about considering this case? This case specifies, or let's look at this example, and we have this for loop and here, and we have this particular function here, and this function has a certain instructions length of the log n, and it's going to be n. And what you can see is that we can just say it's just one line iteration, but if we're going to count all these lines in another function, then it's going to be n multiplied log n iterations. In that case, we have to multiply it, and the answer is going to be order of n log n. So it's this case, right? So actually what we have been doing is that we compared the efficiency of the list, stack, and queue in the previous lecture, previous week. And this was the table, and we just counted the number of retrievals, number of iterations for each operations, right? And after we learned how to formally analyze the algorithm efficiency, we can turn these counts into the big O notations, right? Like this. So we have one retriever. In that case, it's just constant time execution. So we can just say it order of 1, right? This order of 1s and order of 1s, right? Here, I retrievers, and worst case, it can reach the n retrievers, and it's going to be order of n, right? The growth rate is going to be bounded, asymptotically type bounded to the order of n. And by utilizing these big O notations, we can really formally represent the efficiency of a certain algorithm and a certain data structure. And that's the goal of this lecture. We are going to learn many different data structures. In the later of this course, we are going to learn the trees and hashing and the graph structures and all the others, priority queues and so forth. And these all data structures and some of these sorting algorithms have their own efficiencies. In that case, we want to formally represent the efficiencies and compare one algorithm or one data structures to another. And in that process, it's very vital to understand this the efficiency representation technique, and it's called big O notations, right? So there is a further reading on this, and it's great book. It's interesting. It's good book to buy, right? So we have 5 to 61. Actually, it's kind of long reading, but it is worthwhile. So I recommend you to go and read this, right? Luckily, we don't have that much coding in this week, but we have some selection problems and selection sorting problems. So I recommend you go home and type this in your MATLAB, right? Okay, thanks, and see you in the classroom.